All right, let's look at sample test 5. Number 1, what is the closest apparent depth of a coin 5 meters below the surface of a pool? Use n equals 1.33 for water. So we have water, we have a coin that's 5 meters underneath, but it's going to, the light is going to bend as it comes out, and so it'll look like it's got a different depth. Something. So we called this big depth D, something like that. So the apparent depth, little d, was big D over N2, the index of refraction for the liquid or whatever the thing is inside of, and so let's call it, that's water, so that's 1.33, so we got 5 over 1.33. So we'll get 3, so the apparent depth is 3.76 meters. And so which one is closest? Just a little bit closer to C, 4 meters. All right, the wavelength of light that travels through a material depends on the light's color. Yes, the wavelength changes as we go through a material or into a different index of refraction, so we would say true. A. If the magnification of a lens is negative 5.9, you know that. So m equals negative 5.9. We have the rules that if the magnitude of m is greater than 1, then it's larger, right? If it's less than 1, then it's smaller. And if if m itself is positive, then we know it's upright. If it's negative, then we know it's inverted. So this one is larger and inverted. Right? Image is not upright. No. Closer to the lens, DI is smaller than DO. No. Larger, yes. Okay, so it's just the only one that works here is larger, so that would be C. A ray of light strikes a diamond from the air. What is the phase shift of the reflected light wave? All right, so we talked about we have two substances, N1 and N2. If N2 is bigger than N1, then we get, when the light comes in, it gets a 180-degree phase shift or a pi phase shift, right? So basically, this is where a ray starting in N1 and bouncing off of something with N2. So there is a pi phase shift. And so if it was going up, well, anyway, the wave has a shift of pi. So that's A. All right, a ray of light inside film strikes air. What is the phase shift of the reflected light? So we have some, like a thin film, maybe like an air, like a bubble or something, where we have air, and then we have some sort of other substance, maybe water or soap combination, and then it's back to air inside the bubble. And so it says inside strikes the air inside the film. So we're talking about this ray of light inside the film. It's hitting that boundary and bouncing off, and then it's going to refract again when it comes out here. But we're asking about in here, is there a phase shift between this ray going in and then when it comes back out? And so in this case, we've got N1 is equal to air, and this one is inside the film. It's going to be bigger than air, say it's soap or something. N2 is going to be bigger than N1. But now we're starting in N2 and going to N1. And so when we're going from, when we have a phase shift, or we have a reflection from something that has a higher end to a lower end, then there is no phase shift. So this one will be 0. All right, when the reflection of an object is seen in a plane mirror, the image is, so we it's kind of, I guess we started with this, but so it looks like it's behind the mirror. Just draw an arrow, I guess. And it's upright, the same size. Let's see. So it's behind the mirror, so it's on the dark side. And so it's virtual, so it's one of these. And it is upright. When we look in mirrors, we don't see ourselves upside down, so that's B. The image formed on the retina of the human eye is always, and so we have something in here, we have a converging lens, we always get an image that's back inside the eye. It's upside down, and it's on the side of the lens where the light travels after it hits the lens, so it's real. So it's inverted and real and smaller. There we go. So that's a D. Alright, when doing the double slit experiment, we see a collection of small dots separated into larger blobs, light patterns centered around the zero location. What determines, the width of the larger blob? So this is talking about like what we saw in lab. We had something like this, and then we had a group over here and a group over here, and then another smaller group kind of thing. And so we're asking what determines the width, this width. Alright, so remember when we did the single slit, we saw the same kind of thing except for it was solid bands. Alright, and so it can't be that it's the slit separation because we saw the same thing for just one slit, so it must be the slit width. Anyway, if you forget, you can think of it that way to remember. So it is the slit width that causes these causes or determines how far apart or how wide the bright is or how far apart the darks are, which is basically the same thing. Okay, which is the closest to the resolvable angular separation for 500 nanometer light through an aperture 1 millimeter wide? Closest resolvable angular separation. So we had, for a circular aperture, we had that sine theta is 1.22 lambda over d. And so if we want to, remember Raleigh's criterion said that the peak of one, the second one needs to be at least far enough over to be in the valley of the second one, so at that angle where the minimum occurs. And so this equation is for the first minima, and so we want the next one to be that far over, so the angular separation needs to be that. So, and I think you probably have this equation on your equation sheet for the critical angle, or the I guess it was resolvable angle, inverse sine of 1.22 lambda over d. Lambda is 5, so we want inverse sine. So inverse sine of 1.22 lambda is 500 nano, 10 to the negative 9. And divided by d 1 millimeter. 1 times 10 to the negative 3 meters. Alright, so inverse sine 1.22 times 500 negative 9 divided by 1e negative 3. So we get 0.035 degrees. So the closest one would be this one, A. Alright, sorry. Okay, number 10. We look through two lenses at once, one with magnification -5, one with magnification of -5, and one with 0.5. What do you see? Well, let's get the total magnification first. So that's going to be the two multiplied times each other, m1 times m2, so that's -5 times 0.5, so the total magnification is -2.5. So again, like we saw before, if the magnitude is, so the magnitude of m total is greater than 1, so that means it's larger. The combined image is, the image through both of them will be larger than the original object, and then since m total is negative, that means it will be inverted. So it should be larger and inverted, excuse me. So inverted and larger than the object. There we go. A. In Young's double slit experiment, both the distance of the screen and the slit separation are decreased by 50%. What happens to the distance between the same two adjacent bright fringes? Alright, so we've got the equation y, let's call it y sub m in general, is L m lambda over d for bright fringes for the double slit. Yes. Okay? And so, or at least approximately. And so we're saying that distance to the screen, that's L, becomes half of what it was. So we get L over 2 m lambda, and the slit separation d also becomes half of what it was, d over 2. So we see that this is our new ym prime, whatever. And we see that the 1/2 will cancel out, so we get ym prime is just the same as ym, so there's no change, stays the same. A. Right. If the wave from one slit of Young's double slit setup arrives at a point on the screen one full wavelength behind from the other, what is observed? So this is, we have one here, and then the other one is like this, but then it's one full wavelength behind, so they are, should be peaking at the same time, valleying at the same time. So we see this is what we call constructive interference. Totally constructive because they're exactly lined up. Total constructive interference. And so we should see double the brightness, or anyway, a bright spot. All right, the brightest kind of combination that we have. So it would be bright fringe. That would be. Okay. Excuse me. Which color would a thin film of thickness 240 nanometers and n equals 1 before not reflect is what that probably should say, not reflect. Okay, so we're looking for now destructive interference because we're getting not reflected. And it's a thin film, so we have a thickness, T is the thickness, and we have an equation for this. And so this is, we'll assume it's a thin film in air, and so the N of the film is higher than the N of the surrounding material. So we can use our equation for destructive interference. Yep, destructive interference for a thin film. And so that equation is M, some total number, some count, we'll probably want to take the minimum to be just 1, equals 2 times the thickness times N of the material divided by the wavelength of the original light. Yes, we have wavelength. Okay, and so we're going to just assume it's the thinnest film, so we're going to just take this M. Remember, the M is kind of like a counting integer. We'll take the skinniest one, the first M, and so then lambda, what are we looking for? Thickness. So let's solve this for T. So T is going to be lambda over 2N. Yes, so we would have 240 nanometers over 2 times 1.4. 240 nano divided by 2 times 1.4. It's like 85.7. 10 to negative 9 meters. So 85.7 nanometers is our T. It's at least the thinnest T. Whoops, what am I doing here? What color? Okay, sorry. Not reading the problem very well. What color? So that's asking, basically asking us lambda, and we're given the thickness. Okay, we're given T equals 240 nanometers. All right, try this again. So we want lambda, and so let's solve this for lambda. That's even easier. So lambda equals 2Tn. So 2 times T, which is a 240, 10 to the negative 9, times N, which is the 1.4. And so let's do that. Times 1.4. 673 nanometers for lambda. All right, and so our new handy dandy equation sheet has our spectrum on it. So 673. So here's 600, here's 700, 673 looks pretty much red. Red. Okay. How thick? So now it's asking for T. Should a non-reflective coating with N equals 1.4 be on top of glass with N equal 1.5 to block red? So this red now we're taking is 670 nanometers. Mark the closest answer. Alright, so again we're doing blocking red. So blocking means destructive interference, right? Our thin film, or our thin coating on thing has a different equation, right? Because the reflections they both, when it hits the film from the air, there's a pi reflection or pi phase shift, and then when it hits the film from the film to the glass, there's another pi reflection because N equals 1, and then N equals 1.4, and then N equals 1.5. So both of them will have a pi in it. So it's kind of the opposite. Even though they're both destructive interference, this one's going to have the half wavelength kind of number in there to get the destructive interference. And so our equation for this is 2T is equal to M plus a half times lambda over N, right? The wavelength inside the film. And so, lambda over N is lambda sub N, which is the wavelength inside the film. So this is the wavelength of the glass, of the light in the air to start with. And so we want T, let's see, we'll take M to be the smallest. In this case, the smallest M is 0. And so we can say T is going to be divided by 2, so it's going to be lambda over, got a half and a divide by 2, so lambda over 4n. And so lambda 670 to negative 9 is 4n 1.4. Okay, 670 nano divided by 4 times 1.4. Looks like 120 nanometers for the thickness. So that is closest to 120 nanometers. I'll go see. All right. Which of these are the correct ray diagrams for a converging lens? All right, so we're going to look at rays. The rays, one thing to check is if there's a parallel ray on one side, it better be converging to the focal point on the other, and vice versa. So this one looks good, and we've got one going through the center. So that looks like a good diagram. A is good. This one, look at this, it comes parallel and goes off away from center, so that's a diverging, so that's not good. It's supposed to be converging lens. This one has got the converging shape parallel towards the center, but this one has diverging shape following it backwards, parallel, and then it goes off, so this one's not converging. Just not a good diagram. Some converging, some diverging, there's problems there. This one, we have parallel to to focal. That's a converging pattern. Parallel on this side towards the focal point here. This one is focal parallel, but if we follow it backwards, parallel, and then it comes down in, so it's got the converging pattern through the center, so that one looks good. Let's see, this one is parallel focal. This one goes through the center, but this one like goes straight down to the focal point instead of going through the lens. That's not really how we do the diagrams, so that the third ray is not right. So we've got A and D are good ones here. All right. Looking at number 16. Consider a diverging lens with a focal length of 5 centimeters and an object placed 7 centimeters to the left of it. All right, so we've got a diverging lens. I'm getting ahead of myself here, but diverging lens, and focal length is 5. 1, 2, 3, 4, 5. Remember, lenses have 2. 1, 2, 3, 4, 5. 2 focal points, but these are 5, each of them 5 centimeters away. In terms of, we can do the object 7 centimeters. 1, 2, 3, 4, 5, 6, 7. So the object is over here somewhere. This is going to be DO. It says, where is the image? So let's go ahead and do a little math here. So we've got our lens equation. 1 over F is 1 over DO plus 1 over DI. And in this case, we're looking for DI. So DI, just rearranging this, is 1 over F minus 1 over DO. F, in this case, it's a diverging lens, so that means F is negative 5 centimeters. And this is telling us the object is 7 centimeters away from the lens, so that means DO is 7 centimeters. And so we're going to have 1 over negative 5 minus 1 over 7. Alright, looks like negative 2.92. Since everything was centimeters, the answer is going to come out as centimeters, so that's DI. So that's the location of the image. And so for a lens, negative DI means when the light goes through, so which is the dark side? It means it's on the dark side. So which is the dark side? It's this, the light side is the side where after it hits the lens of the mirror, where does the light go? It keeps going on this one, so that's the light side. So the light side's over here, dark side's over here. And so it means this object is over here, 2.92, somewhere over here is where we expect the image to be. All right. Part B, use a straight edge to sketch a ray diagram on the diagram below. Use the dotted line position as the lens. Be sure to include, so I got DI, DO, and F in the lens shape already. Object, this is the object. And we need to get the image and the rays. Okay, so we have 3 rays that we draw. We do parallel focal. So we'll first go parallel here. Try to go straight, parallel, and then focal. So it's going this way, parallel is easy, and then it needs to be a diverging lens. So which focal point, the question is, is it going down here to this focal point, or does it go down here as if it came from this focal point? And so the answer is it's a diverging lens, so it's got to have that diverging pattern, so it needs to be going away from the middle line here. All right, so this would be ray 1, parallel focal. Okay, same kind of thing here for the second one, focal parallel. All right, so if we do we want to do like this? Do we want to go through, they all start at the image, or start at the tip of the object. If we go like this, hit the lens, and then go like parallel, will that be a diverging pattern? No, because look, if we go backwards, it's going parallel here, and it comes to the focal point, so that's not right. Right? We want diverging. So let's look at going to this focal point. So we're going to draw the ray as if it's going towards this focal point on the other side. and then when it hits the lens, or the center of the lens, we're going to go parallel. Okay, and that does make the diverging pattern. If we look backwards, coming along parallel, diverges away from the center. So this is good for ray 2. And then ray 3 is everybody's favorite probably. Just starts at the tip of the object and goes through the center, continues on down. Alright, so ray 3 is there. Kind of hard to tell. So 2 is this one. Alright, so now we've got to figure out where is this image. Well, it's where it looks like these rays are coming from. And so we got to kind of do a dot, dot, dot back here. See where they all come together back here. And really 2 should tell us the answer, but the 3 verify it. And like that, it gets really close to where we said DI is supposed to be. I like it. So that is the image right in there. Okay. So that's good for part B. Part C, calculate the magnification of the lens of part. Of part A anyway. Calculate the magnification of the lens for this one above. So magnification is negative DI over DO. So it's negative DI, we have negative 2.92 centimeters, and then DO was 7 centimeters. Alright, so we get 2.92 divided by 7, and there's 0.417. Alright, so we expect the image to be upright since M is positive, and we expect it to be smaller than the object because M is less than 1 in magnitude, and that's what we see. Part D, a converging lens with focal length of 2 centimeters is placed 3 centimeters to the right of the first lens. Find the position of the image produced by both lenses together. Is it real or virtual? Okay, so we've got another lens, 3 centimeters to the right, so 1, 2, 3. So it's got an axis here, of course, where I have stuff written. And it's a converging lens. There's going to be fat in the middle. Something like that. It's got a focal length of 2. So its focal length is on top of that one. And here. So I'm going to call this F2, and I'm going to just write F2 here also. Okay, so find the position of the final image produced by both lenses together. So when we have 2 lenses, remember the DO for the second one, so DO2, or the object for the second one is the image from the first one. So this is going to be our object 2. So how far is it from the second lens? We've got 1, 2, 3. Well, we've got 2.92 plus the 3. So 2.92 plus the 3 centimeters that the lenses are separated. So it's going to be 5.92 centimeters for DO2. And we've got F2 is a focal length of 2, and it's converging, so it is just a positive 2 centimeters. So we can get our DI just like we had up here. DI is going to be 1 over F minus 1 over DO. 1 over 2 minus 1 over 5.92. Alright, so we get DI is 3.02 centimeters. Alright, and so that is positive, so it's on the light side, so it's on the side where the light goes after the lens. So we got 1, 2, 3, so it's basically right in here somewhere, 3.02. This would be DI2. Part E, add the second lens and its image to the figure. Be sure to include the focal point, all these things. Alright, so we've got this distance here is DO2, and we've got DI2 I just labeled. We've got F2, 2 F2s here. Alright, now we need to get the rays drawn. So the first ray, parallel focal. Let's see if I can find something a different color. So the first ray will be parallel focal, so it's kind of along this parallel from the other one. Parallel, and then focal. Something like that. And then focal parallel. So let's just kind of test out. If we go like this from the tip of the object through this focal point and then parallel, that will have the converging pattern, right? If we come backwards, parallel goes towards the center. So let's do that. Focal, parallel. And then the last one through the center. Okay, so we've got 1, 2, and 3 for here. And it's supposed to be right there. It's pretty close. Is that where we said DI2 was? Around 3. 1, 2, 3. Yeah. All right, so that's pretty close. I2 would be right there. Okay, 3 rays and lens shape. Yes. Okay, find the total magnification. So M total is M1 times M2. M1 is 0.417. M2 we haven't calculated yet, but it's going to be, M2 is going to be negative DI2 over DO2. So it's negative 3.02 over DO2 is 5.92. These are all centimeters, so that's good. Things cancel. So M total is 0.417 times 3.02 divided by 5.92. 0.213, negative 0.213 for a total, M total. Okay. All right, let's go on to next page. Zoom in a little maybe. Okay, consider a convex mirror with a radius of curvature 10 centimeters and an image appearing at 4 centimeters behind the mirror. All right, so convex mirror, so convex radius of 10 centimeters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the radius would be way out. The center of the circle that is the mirror would be roughly out here. So it's a pretty big circle. Not a whole lot of curvature probably. I don't know. Just getting an idea here. Okay, and so radius of curvature R equals 10, so that means F is R over 2 plus or minus. Since it's a convex mirror, it means it's minus. And so in this case, F is equal to negative 5 centimeters. F. 1, 2, 3, 4, 5. So our focal point is there for our convex mirror. The image is 4 centimeters behind, so the image, so this would be our F. And our image position should be here. Hopefully it'll work out to be there. And it's asking for where is the object. And so again, same equation works for mirror. The mirror equation is the same as the lens equation. 1 over F is 1 over DO plus 1 over DI. So DO 1 over F minus 1 over DI in this case. So 1 over -5 minus 1 over 4. Okay, so we got 1 divided by -5 minus 1 divided by 4. -2.22 centimeters. DO. That's not right. DO should not be a negative number. 4 centimeters behind the mirror, so it's on the dark side. So DI should be -4. So put a negative on there. Let's try this again. 1 divided by -5 minus 1 divided by -4. I think I did that wrong. -5 minus 1 divided by -4. 20. Alrighty. That's not good. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to have to change our scale here. So let's make this each block be 2. So this DO is 20 centimeters. So this would be like R. Got ahead of myself. It'll probably be a bit more curved. Oh, it doesn't really matter too much. But then, so F is -5, so 2, 4, 5, so F would be here instead, and the image is at 4, so DI is here, F is here. Okay, so let's try this again. So this is our object at 20 centimeters. All right. And we need some rays. So first ray, number 1, parallel focal. Parallel. Then it looks like it comes from the focal, but it's got to bounce off of the mirror. We'll see how this works. I'm a little worried about this turning out, but we'll try. Alright, parallel focal, ray number 1. Ray number 2, focal parallel. So I'm going to try to go towards the focal point here. But then when it hits the mirror, gotta go off parallel. Come back parallel like that. Ray number 2. Ray number 3, center ray. So we kind of like to go down as much as that was going up, and it's got to come back and hit that and be symmetric. So I'm going to start here. Go down there, and then this one's going to come back to that same position except for down, something like that. This is ray number 3. Alright, now do they come together somewhere close to where the image is supposed to be? So let's get a dotted line going back, dotted line going back, dotted line going back. Well, kinda looks like almost Right there is an image. Alright, so they look like they're coming from over here. Not too bad. Not too bad. Alright, part C. Calculate the magnification of the mirror. Same equation. M is negative di over do. Negative di is negative 4 and do is 20. So 0.2, 1/5. Yep. Negative and negative is positive. No units on magnification. 0.2 is M. If the object is 10 centimeters tall, how tall is image? HY is magnification times HO. So 0.2 times 10 equals 2 centimeters equals HI. And so this is 10, that's 2. Yeah, I can kind of believe it. Does your ray diagram agree with your magnification calculation? And so magnification, so M is less than, magnitude of M is less than 1, and so it should be smaller. I should be smaller than O, yes, check. And M is positive, so it should be upright. And it is, check, yes. I guess yes, image is upright and smaller. That is good. Alright, 18. Consider a double slit setup with a 600 nanometer light and a screen 2.5 meters away from the slits. Alright, so double slit experiment. So for the double slits, what matters is the slit separation. Usually call that little d, but we don't have that. Well, that's what it says. Find the slit separation needed to make the second bright maxima 25 millimeters above the center. Okay, down here we're going to sketch the setup. So let's go ahead and sketch the setup. So we're going to have two slits, exaggerated here, but and then the screen. We're going to have a maximum, and then some minima, more maximum, minimums. Alright, so you want the second bright above center. So this is the first above center, second above center. Alright, for the double slit you got M equals 0, then M equals 1, and then M equals 2. Alright, so this would be Y2. We got distance to the screen, 2.5. We got the slit separation here. Well, that's what we're looking for. Okay, and we're given that Y2 is 25 millimeters above center. Okay, find the slit separation. So for this we have for the bright maxima, so for maxima, constructive interference, we have the equation that, well, d sine theta is m lambda for constructive whole wavelengths. But we don't want, so this would give theta, sine theta is m lambda over d, but we want the y equation. So we got y sub m, we just multiply that by L. Y sub m is like L tan theta, but then we use small angle approximations so that sine and tangent are about the same, so m lambda over d. L m lambda over d. In this case, m is 2, L is 2.5 meters, lambda is 600 nanometers. D is what we're looking for. So let's solve for D. D then is just going to be L m lambda over y sub m. Y sub 2. M is 2. Alright. 2.5 meters to 600 10 to the negative 9 meters divided by 25 times 10 to the negative 3 meters. So D is 2.5 times 2 times 600 times 10 to the negative 9 divided by 25 10 to the negative 3. 120 micrometers, 10 to the negative 6 meters. Okay, find the interference angle for the second order minima of this doublet. So now we've got second order minima. So this is for the minima for interference. We have minima, have the plus a half equation here. Do we have it on here? Maybe we don't have it on here. Nope. For the minima on the interference, so the interference is the double slit thing, then we have that d sine theta. This would be a good one to go ahead and write on your equation sheet. D sine theta is m plus or minus a half. That's not a half. M plus or minus a half of a wavelength. Remember, destructive interference. We want the wavelength shifted so that up and down, one is up while the other is down and vice versa, so they cancel each other out. And so we're going to go for, this is m, I guess second order, we just take second order to mean m equals 2. And so we want the angle, so that's good. So we can just say sine theta equals m, we'll go up plus a half times lambda divided by d. And so theta is inverse sine of m plus a half lambda over d, inverse sine of 2.5 times lambda, which is 600 nanometers, divided by d, which we just got, 120, 10 to the negative 6 meters. All right. Inverse sine of 2 plus a half times 600 negative 9 divided by 120 e to the negative 6. Not very big. 0.72 degrees is theta. Which, I mean, we use the small angle approximation. That's a pretty small angle. All right, let me double check my numbers here. Yeah, 0.716 looks good. Okay, I guess we could call that theta 2, theta m here, theta 2. All right. Sketch the setup, including the interference pattern and the diffraction pattern. Oh, and the diffraction pattern. Yeah, that's kind of hard to do. All right, let's try drawing it. Okay, so this, the interference pattern, or like when in lab we saw the small dots with like this, and then we would have a space of darkness from the from each slit's diffraction. All right. so this is a very big setup compared to what we had in lab to get 25 millimeters for this. All right, because the second, so this is the 0, this is the 1, this is the 2 bright, so this would now be the Y2, 25 millimeters kind of number. And then the second order dark, this would be 0 first, this would be the second order dark. Okay, and so this is the angle, theta 2 to the second order dark. Zero dark, 1 dark, 2 dark, yep. Something like that. So these are the light, the circles are the lights, and these are the darks. Okay, if the double slit is replaced by a single slit, find the second order minima dark fringe if the slit width is 1 micrometer. Okay, so for the dark pattern, or for the single slit, we can kind of think of it as just these blobs being all melded into one kind of a pattern. And for the double slit, for the diffraction, we really just have one equation that might be for everything. That might have been for the double, but really for the diffraction pattern we just look at the minima. And so for that, again, we have D, not D. The diffraction pattern, we're looking at the slit width. We called that A. And so A sine theta equals m lambda. For this, it was really A over 2 sine theta equals m lambda over 2. The 2's cancel out, so we get this. And what are we asking for? Find the second order dark fringe. All right, so we're assume this is asking for Y2 again. Y2 dark. And so we want Y sub m equals m L L tangent theta, but again we're using the small angle approximation, so we got L m lambda over A for our Y sub m equation, and that's what we're looking for is the Y sub m, so we would plug everything else in. I think we got, so L is 2.5 meters, yes. M is 2 second order minima, lambda is still the same, 600 nanometers. And A is this 11 10 to negative 6 meters. All right, so Y sub m equals what? Okay, big numbers, but anyway, 273 millimeters. So that was m equals 2. So I guess that kind of goes, if the little ones were 25 millimeters, the big ones were even bigger, but this is just going for a, it didn't say that the slit width, weren't given the slit width on the double slit, so we're not necessarily comparable. Okay, we'll just go with it. I think that, yeah, that agrees with what I calculated before. Find the angle for the first dark ring for a 11 micrometer round aperture now, not a slit anymore, but a round hole with the same setup as before. Find the angle. All right, so we have the equation for a round hole. We just have the angle equation for the first dark, 1.22 lambda over, I guess we call it D, where D is the diameter or the width of the hole, diameter of hole, since it's now a round hole, which is that 11 micrometers. All right, so theta, find the angle, yes. Inverse sine of 1.22 times lambda, still 600 times 10 to the negative 9 and d is 11 times 10 to the negative 6. So this theta is, no, I didn't mean it. Inverse sine of 1.22 times 600 nanometers divided by 11 micro. 3.82 degrees. All right, 3 degrees. Looks good. All right, next page. All right, let's look at number 18. So we have a thin film surrounded by air on both sides. Index of refraction of the material is 1.11, and it has a thickness given. So this is T, little t is given, and this is N inside the film, right, is given. We'll assume N for air is 1. What wavelength of light will have constructive interference? Okay, so we're looking for lambda. So let's kind of draw the picture here. So we've got N equal 1.111 in the film. Got N equal 1 out here. Equals 1 back here. So the light's going to come in, and one ray will get bounced off. Just thinking of the diagram here. And so is there a phase shift in this new ray, right? Well, we get a phase shift if the N that it's coming to is larger than the N that it's coming from, right? N1, N2, if you want to think of it that way. So N2 is greater than N1, so we will get a lambda over 2 shift, or 180 degree shift, or however we want to think of it. But there is a half a wavelength shift in this first one that's just reflected. So then there's another one that's going to be refracted, and then it's going to be reflected and come out here, and this we're seeing, is there interference here? Interference. All right, and so this one goes through 2t, or well, the thickness is t, but that ray of light travels through 2t. We're assuming everything is pretty much straight up and down, so these angles are highly exaggerated. All right, is there a phase shift here? Well, it's going from 1.11 for N, 111 for N to 1.0, so no phase shift here, because the N is getting smaller. Speed is getting higher, however we want to think about it. All right, so we want constructive interference, so that means we want full lambda differences, right? 0, but we can't get 0, so we're going to have a full lambda difference. And so this ray's already got a half shift from what's coming in. And so this one only needs a half shift more, half a wavelength more inside of here, travel half a wavelength inside of here, so that when it comes back out, it'll be in line with this one. All right, and so we're going to use the equation. Oh, where's my equation sheet? Just to show you where it is on your equation sheet. Here we go. So these are the two thin film equations. We want the one where we only need a half of a wavelength, and so for this one we can get, when m equals 0, we can get it to be a half of a wavelength, right? A half of, if we multiply through by lambda over here, we can see that it's the half is multiplying the lambda, right? And so we're going to be using that equation, so we're going to just say 2t times n over lambda, or I like it actually, 2t times, let's just start over. 2t, the distance that it travels, is going to be m plus a half times lambda over n. So lambda is the frequency, or the wavelength of the light out here, and lambda over n, or lambda 2 or whatever, lambda over n will be the wavelength inside this medium that has the index of refraction n, all right? And so we're using this equation then from figuring out from the picture, and we'll just assume we're going with the smallest one, so let's say m equals 0. All right, and so we want lambda then, we want to solve for lambda, so lambda, to get rid of this half, we multiply by 2 and multiply by n, so we're going to have 4nt, 4nt, guess so. Okay, and so we got n was 1.111 and t was 120 times 10 to the negative 9 meters. So lambda, 4 times 1.111 times 120 maybe negative 9, 533 nanometers. So if we had tried m equals 2, or sorry, m equals 1, we would have a 1.5 factor in here somewhere. That would make lambda smaller. It might also work. So you might get more than one ray of light, or more than one color of light shining here. So I guess we can just go ahead and check that real quick since we're talking about it. So if we had 2t equals 1.5 lambda over n, then we get lambda would be 2tn over 1.5. So 2 times t, 120 e negative 9 times n, 1.111 divided by 1.5. Yeah, so that's 178 nanometers. So that's not in the visible range. So that's only one color gets through. What color is that? If we shine all the colors on, which color is going to get bounced back? Excuse me, 533 nanometers. So here's 500, here's 600, so 533, somewhere around there. It looks kind of pretty much green. Let's say green. Okay, if the film is put on glass that has n equals 1.5, so that air is only on one side, what wavelength will be reflected? What color is this? Okay, so we're going to have the film here again, but now we have glass, n equals 1.5, and this film has n equal 1.111, and the air still has n equal 1. So we got the same kind of thing happening. We've got a ray of light coming, getting reflected, and refracted, and then reflected, and then refracted, anyway, going through, coming back. And so now, both places, so here we have lambda over 2 phase shift, because n's getting bigger, and here again it's getting bigger again, so now this one also has lambda over 2, lambda over 2 shift again. All right, so both of them have phase shifts, and we want maximum. All right, so if we want constructive interference, then we want these to be separated by lambda, multiples of lambda, right? If we were doing destructive, we should do destructive. But anyway, if we were doing destructive, we want it to be dark, then we would want it to be separated by lambda over 2, right? Because destructive is half a wavelength difference, but we're doing, it looks like we're doing the light again. And so in this case, we want the two waves, well, we want this wave, again, we got a thickness t. This ray, wave, whatever, this part of the light travels 2t, and that 2t, we want this one to go through now a whole wavelength, because this one's shifted a half and this one gets a half in here, and so it's like they're lined up basically, and so this one to be lined up after it goes through here has to go through a full number of wavelengths. So we will say m, and again inside, the wavelength inside is lambda over n on the inside. So this is always n of the film, n of the inside for these equations. Okay, so what is it asking? What is the wavelength reflected into the air? So again, we're solving for lambda. So lambda is going to be 2tnf over m. In this case, m can't be 0. It doesn't work, so we're going to use the smallest m is 1, and so we're going to have 2 times t, which was 120, 10 to the negative 9 meters, and f is still the 1.111, and divided by m, we'll just say 1. Okay, so we got 2 times 120 e negative 9 times 1.111 divided by 1. Okay. So this lambda is 267 nanometers. And that's not in the visible range. All right, because visible range, we got 400 to 700. All right, well, let's try m equals 2. So let's do, so this was lambda for 1. Not visible. Let's see if lambda 2 is visible. Lambda 2, and this is the problem with making up numbers here. Okay. 2 times 120 times 10 to the negative 9 times NF divided by 2. That's going to be worse. Okay, never mind. Anyway, we can 120 times 1.111. 133. Okay, so never mind. Can't see. So this one, if we put it on film, it's just going to block colors. We're not going to get the colors coming through. Or at least not completely dark or completely light. Okay, let me just double check my answers from before. Is that what I got? Yes. All right, so should have made up better numbers, or anyway, it illustrates the point. Part D. Find the thickness of film on glass needed to block the reflection of blue light. Okay, so this is the opposite kind of effect. So now we're going to look at this kind of setup still, but now we want to have it blocked. So now our 2t should be m plus a half times lambda over n. All right, so this light travels needs to go a whole wavelength, well, or a half, okay, a half wavelength or 1.5 or 2.5, right? So to get to be out of phase, right? Because they're both shifting, they're both the same, and so this one needs to get another shift. Well, they both have shifts, so this one needs to get 1.5 or a half, 1.5, 2.5 wavelengths to be exactly 1/2 wavelength out of phase with this one, right? Since they both have 2. So, like, if you have both having shifts, or if you have both not having shifts and blocking, you would have something like this. All right, and so what are we looking for? We're looking for t this time. So t is m plus a half lambda over 2n. Okay, so. Okay, and so t, then we can just do the thinnest one, I guess. We'll just go ahead and say, calculate t0. So we're going to have 0 plus a half times lambda for blue. Let's just do the smallest one, 400 nanometers, divided by 2 times our n. This is always n of the film, 1.111. 0.5 times 400 e negative 9 divided by, in parentheses, 2 times 1.111. 90 nanometers. Which is pretty thin. Let's say that was too thin for our manufacturing process, so let's go ahead and see what it looks like for the second option for thicknesses. So we'll do m equals 1, so t1 I'll call it. So everything's the same except for we have 1 plus a half, so 1.5 times 400 e negative 9 divided by 2 times 1.111. Alrighty. So that one is 270 nanometers. Would also have the same effect, right? Sorry. There we go. Okay. Okay, so it looks like I use different numbers for blue. Again, when I don't tell you a wavelength on the screen, you kind of pick it out. You know, there could be, you know, all of this is blue. So blue could be somewhere even to 475 maybe might still be blue. Or even almost 500 might be blue. So a range of numbers would have to be allowed there. All right, let's look at number 19. Excuse me. So, number 19, we have a telescope trying to see Jupiter and its moon, Ganymede, I guess, which is 10 to the 9th meters from Jupiter. Assume we're concerned with viewing red light. All right, so our lambda is this, and Jupiter is 780 times 10 to the 9th meters from the Earth. So just assuming these kind of distances, probably found them on Google. How big is the needed resolution angle? Needed resolution angle to separate Jupiter from its moon when viewing from Earth. So we're just going to have, you know, Jupiter and its moon, probably, again, not drawn to scale, and we have 10 to the 9th meter separation there, and we have 780 times 10 to the 9th meters here, and we're over here on Earth looking, right? And so, and it's asking for what is this angle here, to be able to angle between them so we could resolve them, see the difference. All right, so we're just going to use arc length approximation, or however we want to call it, but or small angle approximation. We could, if we think of it, tangent theta is opposite over adjacent. We could, in small angles, theta and tangent theta are the same, but basically we're going to use the equation that theta equals, if we want to call this h and this d, theta is about h over d. Especially for small angles, we're good. All right, and so in this case, it's 10 to the 9th meters over 780 times 10 to the 9th meters. And so theta is 1 over 780 radians. Let's see here, so 1 divided by 780. Let's put that in parentheses and let's convert it to degrees just because it's nice to deal with degrees. So we're going to multiply it by 180 and divide by pi. Enter. There we go. So we get 0.073. Let's do 346 degrees. All right, is our the angle that the angle that we would need to be able to resolve that. What is the smallest diameter objective lens that could be used? So this is referring to Raleigh criterion. All right, and so we're going to use 1.22 lambda equals d sine theta, where this d is the diameter of the thing we're looking for, diameter of the looking through of the hole. And so we can say then, what is smallest? So that's what we're looking for. What is the smallest diameter of the objective lens? So that's the, you know, the objective is the lens that we're looking through with the telescope. And so d then is 1.22 lambda over sine theta equals 1.22, and lambda was 700 nanometers, and sine of 0.07346 degrees. So let's get our d here, 1.22 times 700 e negative 9 divided by sine of 0.07346. 6, probably keeping too many sig figs, but okay. 666 or 0.666, I guess, times 10 to the negative 3 meters. Oh my, okay. So not a reasonable, very small. Okay, so I said the smallest, so it'd be hard to make a lens that small, but anyway, it's makeable. It's not limiting our ability to make a telescope to see that. Okay, very small number, but we'll go with it. If we are concerned about blue light instead, will a lens selected for red light still work? All right, well, so this was the minimum, so we now get D minimum for blue. Same formula, 1.22, but now lambda is for blue. Let's just use 400 nanometers, the littlest blue, divided by sine of 0.07346 degrees. So we get 0.381 times 10 to the third, negative third meters. All right. So our D is bigger than D minimum. So D up here is bigger than our D minimum for blue. So it still works. We're above the minimum. Okay. Everything is so tiny. It's not hard to be above minimum. Okay. If the objective lens has a focal length, so now we're doing a different, not that objective lens. If we have some telescope with an objective lens with a focal length of 10 centimeters, so FO, what should the focal length of the eyepiece be to get an image angle of 5 degrees? All right, so our telescope magnification stuff, we have an equation here. All right, so M telescope, total magnification, M tele, is negative FO over FE, but it's an angular magnification, so it's theta nu over theta old. All right, so this is going to be I'm calling theta nu, right, where we see when we look through the eyepiece, whereas theta old was just the naked eye theta, which is the 0.07346 degrees. All right, FO, yes, right there. So we are looking for focal length of the eyepiece. So we're looking for FE. So if we rearrange this, FE is going to be, bring that over here, bring these over there, negative FO times theta old over theta nu. Okay. And really we're not worrying about the negative sign, we just want the length. So let's plug stuff in. So we got 10, or negative 10, theta old, 0.07346 degrees divided by the new, 5 degrees. This is centimeters, so our new focal length will be in centimeters. So we'll just do 10 times 0.07346 divided by 5. Again, super tiny. Boy, not reasonable numbers in this problem, but 147 millimeters. It has to be technically negative, but we'll just go with that. Okay, so anyway, hopefully you see the process of how to use these equations and how this goes together. We'll go ahead and stop there.